In this video lecture, we are going to discuss estimation theory, and in particular, we are going to discuss two very used estimators, which are the minimum mean squared error estimator and the linear minimum mean squared error estimator. Before we go into these specifics, though, we should discuss why estimation is an important topic for engineers. As engineers, we are often asked to provide solutions that do not only work for one particular problem in a fixed setup, in fixed conditions, but that in fact need to work in a variety of conditions or a variety of environments. In a way, the solutions we design need to be adaptive to different cases. In order to do so, the estimation of unknown entities, unknown values, unknown quantities that are found in the environment in which our solution should work becomes a crucial task. Some examples of systems in which one needs to do estimation could be the estimation of the user position in a GPS receiver, or it could be the estimation of the direction of arrival of a sound signal that reaches an array of microphones so that this signal can be later either cancelled or amplified, or, for instance, the speed of a ship that is navigating through the ocean and needs to be controlled by a control system. But we will see some more detailed examples later. For now, we're going to define what an estimation problem is. An estimation problem, we can define it as given a set of data, which is here represented by a vector x with n components, given a set of data that can be observed directly, we would like to guess the value of an unknown quantity, which we here generically denote as theta. We would like to estimate the value of this unknown quantity, which we cannot directly estimate. Now, obviously, the data that we observe, and which is going to be the base of our estimation, should bear some relation with the unknown quantity. Since we're working in a stochastic processes course and we're working with probabilities, what we will typically do is to develop a probabilistic model of the data which states its dependency on the unknown quantity theta. But we will see a few examples later. Once we have a model that states the relationship of our observed data x on the quantity theta, then we can define an estimator. Now, an estimator is nothing more than a function of the available data, which is used to guess the value of the unknown quantity. We call the function g here, we call the function the estimator, and for any realization of the data x that we input to the function, we get out an estimate of the unknown quantity, which is the output of the estimator function given the realization of the observed data. Let us now see an example of an estimation problem that occurs in radar theory. Our first example of an estimation problem is going to be that of range estimation in radar. We have here a very simplified drawing of a radar system which consists of an radar antenna and a target, in this case a plane. The target is at a distance r to the radar, and this distance is unknown to the radar and the radar would like to estimate it. In radar theory, this distance is usually called the range of the target. In order to estimate the range, the radar will transmit a short pulse, which we will call here x, Now, this pulse, which is transmitted over the air via electromagnetic waves, will be propagated towards the target. It will reflect on it, and it will bounce back. It will propagate back again towards the radar, and will be received back at the radar antenna as a time-shifted version, which we will call Y. Now, the reflected wave will reach the antenna, the radar, with a given delay, what we will call tau 0, with respect to the transmission of x. Now, this delay we can compute as the distance that the electromagnetic wave has traveled through divided by the speed at which it does. So the distance in this case will be twice the range on the way to the target and on the way back to the radar, so 2r, and the speed at which the wave propagates, since it is an electromagnetic wave, it will be just the speed of light, which we denote with the constant c. Given these conditions, we can actually make a model of the signal y of t that will be observed, that will be received by the radar. This signal will be a time-shifted version of the pulse that was transmitted, which will be delayed by the delay tau 0, which is calculated. It may be received with a smaller magnitude due to the attenuation of electromagnetic waves as they propagate through free space, and we will model this by using an attenuation factor A. And in addition, we will also model the fact that there will be noise at the receiver, and there may also be interference from other systems, from other equipments, and so on. And all of this we will model as an additive noise process W. When this signal reaches the receiver, typically before processing, it will be converted to digital by means of sampling. So if we assume that the radar samples the received signal at a sampling period of Ts, we can describe the samples of the received signal by the radar as just a sample version of signal Y. Now, we were discussing before that the model we make for our data, the samples Y, will be in this case our data, should relate the data to the unknown quantity that we want to estimate. And this is in fact the case, because we can see that we can rewrite the received samples as a function of the range, since the delay of the received pulse depends on the range of the target. Let's just see an example of how the two signals could look like. In this case, the transmitted pulse has been selected as a sinusoidal wave of duration 200 microseconds. And as we can see, the received pulse is a time-shifted version of the original one, where we have a delay here, tau 0, that should be twice the range divided by the speed of light. We can also see that there has been some attenuation, as the received pulse has less amplitude than the transmitted one. And we can also see the effect of the noise process, which for this plot has only been generated as white Gaussian noise. Given all these elements, we can now formulate the estimation problem here, in which our unknown parameter, the unknown quantity, is of course the range R, the range of the target. Our data, or the observations that we have available to estimate the range, are of course the samples of the received signal. We may have a few of them, maybe capital N. And all that would be remaining for us would be the task of defining an estimator for R, which should be a function of the data. Now that we have defined that an estimator is some function of observed data that provides an estimate of an unobserved quantity, we can think of many different functions of the data, and we need ways to characterize whether these functions are accurate estimators of our unknown parameters or whether they are actually inaccurate. This would provide us with the tools to first evaluate different estimators and say which one is better and hopefully pick the one that best suits the needs of our application. And secondly, it would provide us with criteria to design estimators that are optimal according to some of the measures that we will define. For now, we're going to look at three basic measures of the error of an estimator, which are the estimation error, the bias, and the mean squared error. The estimation error, as the name indicates, is simply the error that is produced in one shot, in one go of the estimator. As we can see in this definition, the estimator error is nothing else than the value that the estimator provides minus the value of the true parameter. If we run an estimator once and we have access to the true value of the parameter that we want to estimate, then we can evaluate the estimation error for that realization of the estimator. A measure that is more representative of the general behavior of an estimator is the bias, or the mean error. As the name indicates, mean error, the bias is simply the expectation of the estimation error. So, in this case, rather than evaluating the error of the estimation in just one realization of it, as we did with the estimation error, we take the expectation over all possible realizations of the estimator. If an estimator has a positive bias, this means that the estimator does, on the average, in the mean, estimate values that are larger than the true parameter. It consistently overestimates the unknown parameter. If an estimator has, on the contrary, a negative bias, then this indicates that the estimator tends to consistently underestimate the value of the unknown parameter. Usually, we would like that the estimators we design have the property that their bias is actually zero. And this will happen whenever the expected value of our estimator corresponds with the expected value of the unknown quantity. When this is true, we say that the estimator theta hat is unbiased. Now I said that usually we would like to have estimators that are unbiased. However, the fact that an estimator is unbiased does not really guarantee that it provides small estimation errors in every single realization. For instance, you could think of an estimator which provides estimates that in every shot are very inaccurate, but are equally likely to overestimate and underestimate the true value of the parameter. If this is so in such a case that the positive estimation errors and the negative estimation errors cancel in the average, in the mean, then the estimator will still be unbiased, although it will provide large estimation errors. Another measure that circumvents this problem is the mean squared error. The mean squared error, which we usually abbreviate as MSE, and as its name indicates, it's the expectation of the squared estimation error. Now you can see now that no matter whether the estimator is over or underestimating the true quantity, the squared estimation error will always be positive. Hence, when we take the expectation of the squared estimation error, we will not be in the situation that positive and negative errors compensate each other, and instead we will get a measure that will depend not on the sign of the estimation error, but only on its absolute value. We will next exemplify the three measures of error that we have defined with a simple example.